Okay, so this video is for Calculus 1, related rates. And related rates is basically where you have a relationship between two or more quantities where the rates are changing over time. They usually involve, geometry, formulas, trigonometry, things like that. So for example, suppose they tell you that, oh, there's an oil spill and it's circular. All right, so this is the oil and all that stuff. And since we already know that it's circular, well, we can already assume, hey, we're going to use the formula for area of a circle. Area of the circle is equal to pi r squared. Now, they're telling us that the radius over time of the oil spill changes at a rate of 30 meters an hour. And they want us to figure out, well, what is the change in the area over time, dA dt, when the radius is 100 meters? Well, we have our area formula, pi r squared. Take that derivative with respect to time. Well, that's going to be dA dt equals 2 pi r dr dt. Well, we know the radius and we know dr dt. Well, this one's very straightforward because all we have to do is just plug in the values. So it's 2 pi, radius is 100 meters. Change in radius over time dr dt is 30 meters an hour. And I'm writing the units in because chances are, if you get the units right, then the whole problem's right. So the change in area with respect to time, well, the calculation winds up becoming 6,000 pi meters squared per hour. And if you notice, meters squared, that's area, over hours, that's time, area over time. Area over time. So that means the change in area over time of the oil spill when the radius is 100 meters is 6,000 pi meters squared per hour. So now we're going to do another example. This one's a little more challenging. So now, suppose, actually, let me redraw that line. That is terrible looking. So suppose we have a bin here and sand's coming out of it, and it's making a conical pile, which is a cone-shaped pile. All right, so we have a conical or cone-shaped pile of sand. Well, since it's a cone, we're going to most likely have to use the volume of a cone, which is 1/3 pi r squared h. Now, they tell us that the change in volume over time of the sand pile, dV dt, it's 120 cubic feet per minute. And they also tell us in this case that the radius is 3 times the height, so r equals 3h. And then they want us to find dH dt, or the change in height over time, when, oh, sorry, this thing's going wacky. I apologize. When h is 10 feet. So, well, first off, this relationship is important. We have to plug it in, because if you don't, you take the derivative with respect to t to both sides of the equation, you're going to get two differentials, dr dt, dH dt. The problem is we don't know what dr dt is, so that's not going to work. So The volume of a cone, again, is 1/3 pi r squared h. And again, they're telling us that the radius is 3 times the height. So we want to plug in 3h for r. So 3h squared is 9h squared times h, 9h cubed. A third of that would be 3h cubed with pi. So 3 pi h cubed. So now our volume formula is 3 pi h cubed. And we want to take the derivative with respect to t to both sides of the equation. dv dt equals 9 pi h squared dh dt. Well, we have to find dh dt. We know what h is, and we know what change in volume over time is dv dt. So solve for h, dh dt. So there's two ways you can go about it. You can either just plug in the values and then solve for the unknown, or you can just solve for the unknown first and then plug it in. So I generally, what I like to do is I like to solve for the unknown first, but to each their own, whatever you prefer. So I have the formula here again. And since I want to solve for dh dt, I'm going to multiply by the reciprocal of 9 pi h squared, which is 1 over 9 pi h squared, which is dh. So what that gives me, dh dt is 1 over 9 pi h squared dv dt. I plug in h, which is 10 feet. And the change in volume over time, dv dt, is 120 cubic feet per minute. And to save some time in the calculation, it comes out to 2 over 15 pi feet per minute. Remember, check those units, because feet cubed over minutes times 1 over feet squared is feet per minute, which is approximately 0.042 feet per minute. And the last example that I'm going to talk about is, suppose I have a ladder against a wall. They tell us the ladder is 13 feet, so I'll say L. I'll call it L. And they tell us that the height of the wall is 12 feet. And they tell us that the ladder starts falling down. But also, as the ladder is falling down, it's also going outward away from the wall, from the wall. And they tell us that, okay, well, that the change in the horizontal distance over time, dx dt, is 1/2 foot per second. And they want us to figure out, well, what is the change in height over time, dh dt? Well, if you notice, this makes a right triangle. We can use Pythagorean theorem. So this will be x. Well, Pythagorean theorem in this case would be x squared plus h squared equals L squared. Well, we don't know what x is, but we do know h is 12 and L is 13. So this is a special right triangle, 5, 12, 13. So that means x is going to have to be 5 feet. So we want to take the derivative with respect to t, both sides of the equation. So I'm going to write it down here. So derivative of x squared is 2x, and then of course dx dt. And the derivative of h squared is 2h dh dt. Now this last one, L squared, well, this is the length of the ladder. The length of the ladder is not changing. it stays the same, it's constant. So since it's constant, we treat it as a derivative of a constant. Well, derivative of a constant, any constant, is always 0. Well, now we can solve it because we know x, we know dx dt, we know h. So first things first, using our good old friend algebra, I'm going to subtract 2x dx dt from both sides. And it's going to be 2h dh dt equals negative 2x dx dt. And then to solve for h, I'm going to multiply by 1 over 2h to both sides. So dh dt, write it down here, is going to be negative x over h dx dt. And we plug it in. Well, x we know is negative 5 feet because x is 5. Plug it in. To negative 1 makes negative 5. H is 12 feet. These units cancel out. Dx dt is a half or 0.5 feet per second. So then it's going to wind up becoming negative 5/24 feet per second. So that means as the ladder is falling down, the change in height of the ladder with respect to the wall is decreasing, which makes sense. It's going down. It's changing at negative 5/24 feet per second, which is almost a quarter of a foot per second. And that will do it. I hope this video helps, and I'll see you guys next time. Bye-bye.